Imagine tomorrow would be today. And tomorrow you would have a personal artificial intelligence system, your personal one. And you could ask the question, hey, what is the content of a new document? Could you sum it up for me? And today is tomorrow, because now we're gonna write some code together, execute some code together, create our own individual artificial intelligence, and based on the document Deloitte's Tech Trends, which I've chosen because it is very clearly structured in 9 segments, we're gonna experience what is the answer of our artificial intelligence system. So, here we go. We're gonna use some pre-trained model provided by John Snow Labs, and the general algorithm is BERT, a transformer-based machine learning technique we're gonna apply to our document. As already mentioned, we have 9 segments. The first segment is about turning strategic technology platforms equipped with analytics, automation, artificial intelligence. Then about shift core assets to powerful platforms, to extract more value from data they collect across their supply networks, industrialized artificial intelligence, disrupted data management value chain from end to end, zero trust architecture, remote work, digital meets physical, digital interaction in everyday life, and diversity, equity, and inclusion. Those 9 topics we try to reproduce with our little artificial intelligence system. Here we go. Here's the code. At first, I run this on a local PC with the Windows 10 Home Edition. I downloaded JupyterLab. We're gonna do this in Python 3. And I created a very special environment within JupyterLab with PySpark 247. And if you already have a Spark or a PySpark environment implemented on your local machine or in the cloud with Databricks, for example, you have to downgrade Spark to 247. Otherwise, the code will not work. So we start with importing the typical functions. We're going to load our sentences. We're going to load our sentence tokenizer, the word tokenizer. We load the stop words of English. And if you have some personal stop words you want to include to the list, just comment this line of code. And off you go. I have my sentence here in a text file I extracted from a PDF. We convert it to a list where each element of the list is a sentence. And we convert it further to a Panda Dataframe. We end up with 1,821 elements of our list, where each line of or which element of our list is a sentence. Now to the critical part of our little artificial intelligence system. We have to incorporate the intelligence. And as you can see, by John Snow Labs, they have run a lot of models, of pre-trained models for sentence embeddings. You can think of it as a car. You might have here a Toyota Corolla, you might have here Mercedes-Benz, you might find some Porsche. How you drive the car and where you drive the car depends on you. This just provides the platform intelligence for us. So we're going to load our platform intelligence, our car, and I've chosen a medium-sized car, 400 MB. It's called BERT Base, and it's downloaded in 4 seconds. Just have to perform some transformation, but we end up with a Panda Dataframe where the heading of our column, unfortunately, we have to call it text, otherwise the algorithm would have a problem identifying the column we want to apply the embedding to. Here we have our sentences. And the next step to do is take our Panda Dataframe file, say we want to have an output level of sentence. so that each and every sentence gets a specific embedding, and we do this on the BERT base level. And here we go. Since I do not have an NVIDIA graphics card, so I cannot use any CUDA cores or anything at all, so all the work is done by a 6-core CPU from AMD, less than $200 at home. So if you have a gaming computer at home, no problem to run this program on your computer at home. It's gonna take some time. And after 1 minute and 15 seconds, we now have the result. A Panda Dataframe where for each sentence we found a perfect sentence embedding. Now what you're gonna notice here that suddenly we have 1930 rows. Remember that the output level should be sentence. And when I checked all the sentences, I found that in one line I had 3 sentences with a question mark. It was not identified as a full stop by the system, but having 3 sentences with a question mark in one line, the system is intelligent enough to say, okay, these are 3 separate sentences, and it can happen everywhere in the system. So in the end, we end up with 1930 sentences with full stop and question mark. Of course, you can apply BERT large even to your PC at home. 24 layers, 16 attention heads, and about 340 million parameters. Since it runs on Spark, my CPU with 6 cores, 12 thread, immediately runs at 100%, but it's going to take you quite some time to execute it. You have to calculate 5 to 10 minutes, depending on the on your CPU back home. Or if you have a GPU or a TPU, of course it will run much faster. So this is our result. And we have a visualization here to sum it up for each and every sentence in one row in our Panda Dataframe. We have a very individual embedding. It's a list of, if you want, coordinate systems. And since it's pre-trained, we don't know the dimensionality of the system. So to check it, we see that here we have a coordinate system in a 768-dimensional topological space. Be aware, we are not operating in an Euclidean space. There's no Minkowski space, there's no dot product defined. The distance function here is completely irrelevant. This is a really artificial topological space. You cannot apply the standard distance measures on it. We can save it to a file. The nice thing we can do, since we have now a complex system with coordinates, if you want, we can calculate the cosine similarity of all the data points in the cloud. And we're going to do it here. Wow, just 52 milliseconds. And I choose sentence number 16. This is sentence number 16. For enterprise technology, we spotlight the importance of aligning corporate and technology strategy. And the answer of the system with the intelligence we downloaded from the internet, from John Snow Labs, the system tells us, and these are the sentences that I think based on my pre-training, these are closest in the meaning to our sentence number 16. The nice thing about this, you can have a sentence that's not part of the original body of documents. So I have my sentence here, trust machine learning, university. And you're gonna say, yeah, strange sentence, but I can calculate the embedding of this sentence. And if I have the embedding of this sentence in 768 dimensions, I can again calculate the cosine similarity with all the other sentences in the document and come up with an answer. Interesting, since we have now a sentence of only 4 words, you can see that the answer of the system is a sentence with 2 words, a sentence with 3 words, a sentence 3 words. And since we have BERT as the underlying, if you want, algebraic technology to it, BERT uses wordpiece models that are content sensitive of the sentence itself. So let's say we have here 2 times tools for equity. If you have a sentence 1 with the word water in it and a sentence 2 with the word water in it, and the sentences are different, BERT will assign different embeddings to the same piece of word water depending on the content. So within BERT you will have, it's not duplicates, it's multiples of the same words or the same pieces of word, depending on the meaning of the sentence. But here, of course, we see that the problem of padding will come in place. To make things easy for us for the calculation, we're going to apply some methodology from mathematics, algebraic topology, to reduce our dimensional array, our dimensional functor, if you want. There is some beautiful code, and you see the API of this code here. It's called UMAP. And if you apply this code, you can reduce the dimension from 768 to, like I decided here, 5 components. The only other parameter you have to define is the neighbors of a specific embedding, since again, we're in a topological space, there's no distance function defined, so we define here a fuzzy set of epsilon environments, a kind of a topological space which will induce a specific metric for each and every point in our point data cloud. And we end up with each and every sentence with a 5-dimensional coordinate set. Next thing, we can cluster the sentences. And you're going to say, hey, great, perfect, there's an algorithm to cluster it, but to end up with 9 clusters, 0 to 8, like I want, because in the document for human readers, there are 9 clearly separated segments. We have to set the minimum cluster size to 60 and the minimum sample size to 5. So we have to play around a little bit with the parameters to come up with a solution that's within the radius of error that you want to examine. Also, and this is the speciality of this algorithm, you come up with a cluster -1. And this tells you there are sentences that the system decided I cannot assign it to any of the other 0 to 8 clusters. This I regard as noise. And if you look, we had a set of 1930 sentences, of which 525 the system says these sentences are noise for me. They do not form a cluster given the preconditions of the clustering. And then we have for cluster number 8, for example, 346 sentences and so on. So you put it in a data frame, you make it nice, and you get the idea, okay, if I have a coordinate system, can I visualize the data? And of course, so we run UMAP now in 3 dimensions. We apply the clustering to be a little bit more accurate from 5-dimensional space. We put it all together. Takes a little bit of time, but what we end up with is for each and every sentence, we have a data frame that tells us this sentence belongs to cluster number 3, cluster number 7, cluster number 5, and each and every sentence has a set of coordinates in X, Y, and Z. So next, you can look at the individual clusters, but right now we're gonna wanna have a view at the visualization of our cluster. And here we are. Those are all the sentences, except for the noise, which is not part of this visualization. And each dot is a sentence. And what you see, we have a real nice sphere of clustering objects here. And then you could say we have 2 outliers or 2 elements where if you regard this as a graph, as a connected component, these are outliers we're going to have a look at. And let's see what these sentences are. Cost center value driver, technology scale, trust for billions, cyber. You see here 5 words, 3 words, 4 words. Again, we have here that those short sentences tend to cluster. Here, a sentence with one word. If you have a huge amount of sentences, this will not be so prominent. But if you only have 1,800, 1,900 sentences, maybe we should clean up our sentences at the input level. So we could ask, hey, a sentence with one word, is this an illegible set that we want to add to our input set? Because clearly you can see from the content of the short sentences that a lot or several topics of our 9 segments are clustered here within this one cluster, and this is not what we are looking for. So the length of the sentence seems to override the importance of the thematic clustering. Again here, 4 words, 3 words, and if next the result, one challenge here, how? Oh well, great, yeah. So we have to clean up our sentences to get more meaning into the sentences, and maybe we eliminate sentences with just one word. If we would do this, and this is part of the next video, we would get all the sentences here in a more coherent way, because the clustering of this sphere here seems to be quite nice. And if you notice, for example, the green set, here we have 2 green outliers. And you might ask, hey, why does the system identify these 2 points belonging to the green cluster? Remember, the clustering we have done in 5 dimensions, which maybe are a little bit more accurate than the clustering in 3 dimension, because we lose some information if we go from a 5-dimensional space to a 3-dimensional space. So if you see minimum number of outliers here, no problem at all, or you do the calculation, all of them in 3 dimension, then you should reduce these artifacts. But as you can see, the sentences here are too informative. There's too much information in it. And the next step would be for a personal artificial intelligence system that we say, okay, what are the key words? What are the key components of all the sentences in the red cluster? What is the key word? What are the key 2 words? Or maybe, let's call it bigrams or trigrams. What are the main 3 words that define the cluster? And there's a very nice element of code we're going to apply, and it is by Martin Grotendorst, and here's his reference in GitHub. Have a look at it. It's a beautiful algorithm. I modified it a little bit for us here, but it provides us with exactly what we are looking for. Again, just for Jack, we have here the label -1. This is our noise level, 525 sentences, and then our other clusters with the amount of sentences here. We exclude noise, and the answer of our personal system is now that we end up with 9 clusters. These 9 clusters have the amount of sentences. Cluster number 8 has 346 sentences, and within this cluster, the top words of the sentence, and not only words but also bigrams and trigrams, are these. First, zero trust, low code, machine learning, cloud-based, real-time, data management, supply chain, COVID-19. Yes. Based on the pre-training, you can see here that you have numbers clustered 18, 24, 19, 24. This is also where you have the very strong influence of the pre-trained system that now defines the outcome of your analysis. Zero trust here, zero trust here, and you remember BERT. BERT is content specific, so you can have the same bigram here and the same bigram here, but the system decided that the meaning of the sentence where zero trust is used is different and belongs to a different cluster. Supply chain, value driver, cost center, finance risk, industrialized AI, bespoke experience, adjustment needed, chief risk officer, equity, inclusion, digital workplace. You can see here that digital workplace and equity inclusion, the system regards as belonging to one system. Also within the document, it is clearly separated in different segments. So this opens up the question, hey, based on the pre-training knowledge, the intelligence we downloaded, is it possible that this presentation of 9 segments can be further simplified? Is there a data manifold that is simpler, that has a smaller number of aggregate clusters that would summarize the content of the document in a more stringent way? And this is the question for the next video. Thank you.